Okay, so let's get started right away with this idea of, visualizing events. So let's look at our situation. I'm going to imagine that I have some sample space here. Okay. Okay, so this is the set of all possible outcomes. Okay, and I'm going to have some event, which is some subset of it. So I'll take this kind of circular area here. We'll call that A. Okay, and then we'll say that A here is this region. Okay, that A is that region. And then that's the red region. I probably should have gone the other way around actually with my colors, but then this green shaded region is what? Okay. Well, S is the total sample space. Okay, and we know that the probability of the sample space has to be equal to 1. Okay? And we know that the probability of A is somehow represented by the red area. Okay? So then A is the red area, set shaded in red. Okay, so set shaded in red. What could I? So A is the situation where this set here is the set of all possible outcomes where A occurs. Well, then what is the green area? Well, the green area, the green shaded region, is where A does not occur. Okay. Okay, so this red shaded region is the set of outcomes where the event A occurs. Okay, so S could be the sample space for rolling a die. A could be that I get an even roll. Okay, and then the green area would be where I don't get an even roll. Okay, and if I don't get an even roll, then I would get an odd roll. Okay, so let's look at simple example then, okay, or a simple consequence. Okay, so this green shaded region is where A doesn't happen. Okay, so the probability of not A, okay, the probability that A does not occur, okay, is going to be somehow related to the probability of the total sample space, which we know is 1, and the probability of A. Okay, and it's going to be equal to 1 minus the probability of A. So a way that you might think about this is if you think about this as kind of representing probability in terms of area, the total area of the box S would be 1. The probability of the sample space would be 1. The probability of A is like the area of A. And then the area of the green region, the region where A does not occur, is what? Well, that would be 1, the total area, take away the area from A, or 1 minus the probability of A. Okay, so that is called the not rule. Or possibly the complementation rule. Okay, so let's give an example. let's say I roll a d6, six-sided die, okay, and we'll let A be the event that we get a 1 or a 2, okay. A is the event that we get a 1 or a 2. Well then, what is the probability that I don't get a 1 or a 2? Well, that would be the probability of the total space. The probability of not A would then have to be 1 minus the probability of A. And we can see here that if all of the outcomes are equally likely, that is to say that this die is fair, then there are 2 outcomes here, and then I could go back to using the equally likely outcomes definition. This would be 1 minus 2 over 6, which would be 4 over 6. That's not looking all that good on the page there, but that's 2 over 3. Okay. Okay, I just paused there for a moment. Let's resume again. A way of thinking about this, say for example, if I told you that there is a 97% chance that it'll rain tomorrow, then you would naturally know that there would be a 3% chance that it wouldn't rain tomorrow. So this complementation rule is fairly simple and straightforward. And if we think about things in terms of the picture, it's very easy to visualize. Okay. So let's talk about mutually exclusive events. Mutually exclusive events. So let's draw my sample space here. Okay. So this is S here. And let's say that I have a set which is A, and I have a set which is B. And these do not overlap. Okay? Let me get some color here. Okay. So we'll color A in blue this time. We'll cover B with green. Okay. And then the remaining area we'll make red. Okay, so we can see here that A and B are 2 separate events. Okay, they're 2, and when I say separate, I mean that they are separated. Okay, there is no possible outcome in A which is also in B. Okay, so that's what I mean by mutually exclusive. I have my set of all possible outcomes, and A and B are called mutually exclusive events. Mutually exclusive events if they share no common outcomes. Okay, if they cannot occur together. If they cannot occur, and I'm going to have to move down into another line here. Simultaneously. Which is a very long word to try to write on an A4 page this big. Okay. So these cannot occur simultaneously. If I am in A, then I am definitely not in B. If I am in B, then I am definitely not in A. Okay. And now okay. That's one possibility for mutually exclusive events. In general, Usually, sorry. Usually, events, or generally I should say, generally, rather than usually, events may overlap. So what would that look like? Okay. Okay. So this is my sample space. This is going to be A here. This is going to be B. Okay. Okay. And we'll give these different colors here. So I'll cover B in green, same as before. Okay, I'll cover A with blue, same as before. Okay, and the common region, the shared region to both of them, is that red region there, that small red region in the middle. Okay, so that's what I mean by overlapping events. So this is the event here where A occurs, that's this left circle, okay, this left circle which includes the blue and red. The event that B occurs is the right circle, the right region here, which contains red and green. Okay. By the way, if anyone's colorblind, this is red, this is green. Okay. Red and green color blindness is apparently quite common, but I'm not colorblind, so hopefully this is still helpful. But the area in the middle is the area where they both occur. So A occurs in this middle section and B occurs in that middle section. Okay. So a fairly simple question then is, well, how do I find out the probability that A occurs or B occurs? Okay. How do I work out the probability that A occurs or B occurs? Well, this is a little tricky. Okay. It's not too bad, but it takes a little bit of thinking about. Okay. So let's say that I said, okay, well, let's take the probability for A, which we'll assume is some number we've worked out, and we'll take the probability for B. Okay, which we'll assume is some number we know. Okay, well, now let's look at the situation. I've counted all of A and I've counted all of B, which means when I counted PA, I counted the blue region and the red region. When I counted P of B, I counted the red region and the green region, which means I've counted the red region twice. Okay, so I need to get rid of that overlapping region. Okay, I need to remove it so that my count is back to normal again. Okay, so then I'm going to subtract away the probability of A and B. Okay, so what is that? That's blue and red plus red and green, and then take away red because I've counted red twice. So this is the addition rule. Okay. Okay, that's my addition rule. And here's an important thing to notice. In this case, when there is an overlapping section, okay, an intersection, a non-trivial intersection, I have to subtract away that intersection. But for mutually exclusive events, there is no middle section. So the probability of A and B occurring would just be 0, and I would just have the probability of A and B. Okay. So then, what would that look like? Okay, well then, the probability of A plus B is equal to the probability of A or B if A and B are mutually exclusive. Which is to say that the probability of A and B is 0. Okay, so that's the idea of the addition rule. Okay, and we'll give an example of that in a little while, but there's one more thing. Okay, and we noticed here, okay, I talked about how to find the probability of A or B. Okay, so we've worked that out. Now we can get rid of that question mark. Now we know the answer. Okay, the probability of A happening or B happening is the probability that A happens plus the probability that B happens minus the probability that they happen together. Okay, now you might ask yourself, okay, so if I know PA and I know PB and I know the probability of A and B, I can go and find the probability of A or B. But how can I go and find the probability of A and B? Is there an easy formula for that? And the answer is not usually. Okay. This is where we have to talk about something called independent events. Okay. So independent events. Okay, so two events are thought of I should say thought to be independent they're thought to be independent if the occurrence of one I think it's 2 or as an occurrence. Okay, does not in any way affect the occurrence of the other. Okay, so let me grab some props here. I have a red dice and I have a red die and a purple die. Okay, and let's say that A is the event that I roll an even number on the red die, and we'll let B be the event that I roll an even number on the purple die. Okay, well, does the outcome of the red die in any way affect the outcome on the purple die or vice versa? And the answer we expect is no. Okay, why? Because there's no magnetism between these. They are not telepathically linked. One does not tell the other one what to do in any way. If I roll the red die, and there I get a 5, okay, that tells me nothing about what will happen when I roll the purple die. Okay, so those would be examples of independent events. Another example would be, say for example, that I decided to draw a card from a pack here, and then I decided to flip a coin. Okay, so my experiment is flip the coin and draw one card. Okay, and then the question is, let's let A be the event that I get ahead, which in this case is this Walking Liberty here. And let's let B be the event that I get a spade. Does the coin flip tell me anything about the card selection? No. Does the card selection tell me anything about the coin flip? No. Okay. So those would be examples of events that we would believe to be independent. Okay. Now, the unfortunate thing about this definition is that it is not a mathematical definition, and it's also hard to tell if events should be independent or not. Okay? So, in mathematical terms, okay, mathematically, we say that A and B are independent events and this is the definition that a mathematician would use. The probability of A and B is equal to the probability of A multiplied by the probability of B. Okay? Now, let's say, really silly example, is the event, say I select somebody at random from a population. A is the event that they are, I don't know, a fan of George Michael, and B is the event that they are over 6 feet tall. Okay? That's, I assume two completely separated events with no, not separated events, but two independent events, one that does not in any way influence the other. But I don't know, okay? So let's say I know that the proportion of people who are fans of George Michael is, say, 3% of the population, and the proportion of people who are over 6 feet tall is, let's pick a different number, let's say that 25% of the population is over 6 feet tall. I'm making that up. I have no idea if that's true or not, and I have no idea how many people identify as George Michael fans. But if 3% of people over 6 feet tall are George Michael fans, then being a George Michael fan doesn't influence your height, and being over 6 feet tall doesn't influence whether you're a George Michael fan or not. In the same way, so that was if 3% of people over 6 feet tall are George Michael fans, then that's the same as the total population proportion, and it doesn't make any difference. Another way of saying that is, well, 25% of George Michael fans would still be over 6 feet tall, which is to say that the proportion, the height breakdown of George Michael fans is exactly the same as the height breakdown of everybody else, that there's no influence. Okay? And that's the idea of independent events. Now, often things that we might think of as being independent, and I took a ridiculous example there, are actually not independent. Okay? So, for example, let me try to come up with an example that you might initially think is independent, one which, a way that it might not be true. Let's say, for example, that I had the same kind of situation. I'm interested in whether people are fans of video games or not. I don't know. Or let's say that they're likely to spend more than, that the person has spent more than €100 on video games in the last year, and we'll let B be the event that they are over 6 feet tall again. Okay? Well, typically, it's not always the case, there are plenty of female video game fans, but typically most video game fans are male. That's why a lot of video games are targeted towards men because more men buy them. Also, men are more likely to be taller than women because, we are a sexually dimorphic species. There are differences, at least physically, between men and women. As a result of that, it's entirely possible that being taller means that you are more likely to be a man, and if you are more likely to be a man, it's more likely that you are, somebody who's going to spend money on video games. Now, that may not be true, but it's an example of a rationale which might show that these are actually not independent events in that example. Okay? So we'll talk about independence, exclusivity, all of that with some concrete examples in the next lecture, next video lecture, and we'll get on to doing some calculations. But now we have a good understanding of the basic framework that we're following. Okay, we have an understanding of the rules. We know how to negate. We know how to take an event A or an event B. And in the event that we have independence, we know that we can work out the probability of A and B, given the probability of A and the probability of B. Okay, so we'll leave it there, and I'll upload another video soon.